In the last session, we finished with unit number 2. That was basic concepts of the metal cutting, single point cutting tool using material removal. And this unit number 3 is going to focus some advanced things in the same area, that single point cutting tool and metal cutting using that single point cutting tool. So in this unit, we are going to talk about thermal aspects in the sense what are the sources of heat generation in metal cutting, what are effects of that heat generation on cutting tool, workpiece, or overall machining process, and how to control that heat generation. That everything we are going to discuss in this unit. Additionally, tool wear. We know that cutting tool is expected to hold its cutting edges for maximum possible duration, so that you can have better productivity, better surface finish, better accuracy, and all. If that tool wear is beyond expected range, or that tool wear is more compared to expected range, then that is going to hamper the overall machining process. So what are the forms of tool wear, what are the causes of tool wear, and how to control that tool wear, everything we are going to talk about. And finally, the term machinability. So this machinability we discussed in unit number 1, that is abrasive machining processes. We called it as a grindability. So same thing we are going to talk here also, but here we are going to focus it on single point cutting tool machining. So machinability in the sense various response parameters are there, like surface finish, material removal rate, heat generation, microstructural changes occurring in the workpiece because of that heat generation and all. These things has to be in acceptable range. Means MRR should be good enough, tool wear should not be that much, it should last uh, for the longer duration, then surface alteration should not be there. And when all these parameters are within acceptable range, then we can call it as a machinable material or machinable condition. So that term we are going to discuss in terms of machinability. Now before beginning with this syllabus, let's talk about the objectives, why this unit is there, and what we are going to be studying in this unit. So the first thing is we are going to discuss the effect of temperature generation in metal cutting. We know that whenever material is heated, it is expected to soften, it is expected to expand also. Some expansion is also going to be there whenever you heat the material. So that softening is there, expansion is there. Is it going to have some negative effect on the machining performance, or it is going to be beneficial? Because if material is getting softer, then we can easily cut it, right? But what if that heat generation is softening the cutting tool also? Then that is not desirable, right? So that way we are going to study the various effects of that heat generation when you discuss the overall machining performance. Then second, explain the temperature distribution in metal cutting and various deformation zones. Now, when it comes to heat generation, that heat generation is going to have certain distribution. Means overall workpiece material or overall cutting tool is not going to be exposed to a same temperature. That temperature gradient going to be there. At certain regions, temperature will have maximum value, and as you go away from that point, the heat is going, or temperature is going to be keep on decreasing. So that distribution will be discussing, and the sources of that heat. why that heat generation is there and where exactly that heat generation is there. That is nothing but the deformation zones. That deformation is nothing but the source of that heat generation. So we'll be talking about various deformation zones also as a source of temperature. Then enlist and explain various temperature measuring instruments. Now till this point we will be very much familiar about the effects of the heat generation. Most prominently, all the effects are negative. Those are going to hamper the machining performance in overall. So to keep that temperature range within acceptable limit, first we need to know that temperature range, or we need to have an idea about the magnitude of the temperature first. And to know that magnitude, we need to measure the temperature. So what are the devices that are used to measure the temperature in case of these machining processes? Their working principles and their applications we'll be talking about. Then describe the tool life concept and various types of possible tool wears. So tool life concept in the sense, if I get a new tool and start machining with that cutting tool for the duration for which I can keep using that cutting tool in terms of number of hours, number of minutes, that is nothing but the tool life. Alternatively, the amount of material that I can remove with that cutting tool, that is also tool life. Or the number of products that I can machine with this with that single point cutting tool, that is also nothing but the tool life. So that way we are going to discuss the tool life concept. And then types of possible tool wears. So when I say tool life, or when I say the number of components that I can machine with that single point cutting tool, I mean before throwing that tool, or before observing a certain amount of wear on that cutting tool, what number of components I can machine by using that cutting. That is nothing but the tool life. So that possible tool wears we need to discuss. And tool life criteria. So once that amount and nature of wear on the cutting tool has observed, it says that beyond that point we should not use that cutting tool. Either we should regrind the cutting tool, or if you are using insert, then you should replace the cutting tool, but you should not continue with the same tool, right? Once you have that wear on the cutting tool, and observing that wear on the cutting tool is nothing but the tool life criteria. Once you have got that much amount of wear or that nature of wear on the cutting tool, either go for regrinding of the cutting tool or simply replace the cutting tool. The next, enlist various tool materials commonly used and identify their classes. Now, when it comes to selecting a cutting tool material, you have variety of materials available out there, right? Starting from the carbon steel to a diamond. Diamond is the hardest material possible, or hardest material available out there. So starting from carbon steel to diamond, in between there are variety of materials available. Alloys are there, ceramics are there, or composition of those materials are also there. So out of all these materials, when it comes to selection of the particular material, we need to uh, consider certain conditions. Which material you are machining, at what machining speed you are machining, what type of surfaces are desirable, what type of accuracy is desirable, and depending upon all those things we need to consider the tool material, right? Because of its properties, because of their availability, because of their cost also sometime, right? All these things has to be justifiable, and then you can select that material for certain removal application. Next one, talk about the machinability concept. So as I just discussed on the slide one, machinability concept in the sense, if I consider a simple machining operations, if this is a machining operation, there are going to be certain input parameters and there are going to be certain output parameters. So input parameters are the parameters that you can control. The workpiece material is there, tool material is there, machining conditions are there, like feed, depth of cut and all. Then cutting fluid is there, application of cutting fluid is there. All these parameters that you can control are called as input parameters, and there will be certain output parameters that you can call as a response parameter. So what are those response parameters? Material removal rate would be there, surface finish would be there, accuracy would be there, then material alterations would be there. All these parameters are called as response parameters. So it is expected to have all these response parameters within acceptable range. And when you have that parameters in acceptable range for that workpiece and cutting tool combination, then you will call it as a machinable combination. Means by using that cutting tool, when you are machining that workpiece, all the response parameters are within acceptable range and you can continue with that combination. So that way we will call it has a better machinability. And if these parameters are going to have negative values or values beyond acceptance range, then we will call it as a poor machinability. Okay. Then last one, tool coatings. Tool coatings, cooling fluids, and their method of applications. So when you use a cutting tool, instead of using cutting tool directly, you can improve its properties to have better response values. That is all the output variables that we just considered. So how you can improve the existing cutting tool? You can coat its surface. Now that coating selection will be dependent on certain parameters. What those parameters could be? The amount of heat to be absorbed by the cutting tool. If you want to minimize that one, you can go for certain coating. If you want to reduce the friction, this is amount of heat, then you want to reduce friction the friction between cutting tool and workpiece, that I want to reduce, then I will go with certain coating, right? Or if I want to have, when its temperature of the cutting tool increases, as we discussed earlier, there might be a reaction, chemical reaction taking place between cutting tool and workpiece material. And what I want is that reaction should not be there. So I will coat this surface with certain material so that it will eliminate this reaction at elevated temperature. So that way you can improve the properties of existing tool by providing certain coatings. So that coatings could be ceramic or some alloying element, likewise, right? Then cooling fluid. Now, cooling fluids, also called as cutting fluids, also called as coolants. So you can call anything. Now, the purpose of application of those cooling fluids, cutting fluids or coolants, there are three main purposes. What are those three main purposes? First one is disposal of chip. When you are machining certain workpiece with certain cutting tool, the form chips are need to be taken away from the machining zone. It should not stay there once it has been removed from the workpiece material. And this could be supported by applying the cooling fluids. That is the first application. Second, from the name itself, it is expected to provide certain cooling. So, to decrease the temperature in the machining zone. Second application is decreasing the temperature. And third one is providing lubrication between tool and workpiece. So when you or when the cutting fluid applied provides lubrication between tool and workpiece, this is going to reduce the friction, and a reduction in friction will result in reduction in temperature or reduction in tool wear also. Okay, so these are the purposes behind the application of cutting fluid. And last one is application of cutting fluid. Now application, again there are certain methods in which you can apply cutting fluid. What are the various methods? The first one, simply flood the machining zone. Flood the machining zone means provide large amount of cutting fluid through nozzles and all, so that the whole machining zone will be flooded with the cutting fluid. So large amount of cutting fluid we need to provide. So that is flood cooling. Second, mist cooling. So create a mist of that lubricating fluid and provide it in the form of spray. So minimum fluid need to be provided. You can have better effect also compared to this flooding or flood cooling, because here the amount of fluid that has to be provided is very large, and using that large amount of cutting fluid, then there might be a difficulties in disposal of that cutting fluid also. You cannot simply throw that cutting fluid open in the atmosphere, right? Because of that various constituents that are used to making the cutting fluids. Some oils are there, water is there, then some surfactants are there, cleaning agents are there, and because of that you cannot simply throw that cutting fluid in open atmosphere. You need to dispose it properly. So mist cooling would be there. Or additionally, when you use a cutting tool to remove the workpiece material, usually what we do, we provide passages in the cutting tool itself, and through which you provide that cooling fluid. So what will happen? You can provide cutting tool exactly at the desired location. You can have better uh, results, like better penetration of cutting fluid into the cutting zone, so that heat disposal would be better, then chip removal from that zone would be better, right? But it has got limitation also. What happens when you use this third method? As you are providing passages in the cutting tool, you are making cutting tool weak. Okay, so by this method you can get better results, but there is some negative effects on the cutting tool strength also. So if you can maintain the strength within desirable or acceptable range, then you can go for this third method also. This method is called as through tool cooling, because we are providing coolant through cutting tool itself. So that would be the third method. Okay. So first one is effect of temperature in metal cutting. Now we know that, or we have an overall idea that this heat generation is not going to be desirable at all. Okay, this is known to us. Now in what senses it is undesirable? The first one, the temperature generation lowers strength, hardness, and stiffness. Additionally, it decreases wear resistance also. So when you select a cutting tool, you think of these properties, that tool should have enough strength, it should have enough hardness, it should be stiff enough, and it should have better wear properties, right? But when there is increase in temperature beyond certain limit, this temperature increase is going to have negative effect on all these properties. So strength might decrease, hardness might decrease, stiffness might fall by some value, wear resistance also might fall, right? So all these things might happen with a cutting tool, and that way it is completely undesirable. Additionally, the thermal softening of the cutting tool may happen, and in worst scenario, that may result in plastic deformation also. So cutting tool might deform plastically because of the extent of the heat generation. That is going to be worst scenario. You won't observe it regularly, but that also could happen. So these are the various effects with the cutting tool. Next, we know that whenever temperature increases, it is going to expand the material. When you heat it, it will expand. When you cool it, it is going to be contract, right? Now, additionally, as I said, this heat distribution, or if this is a single point cutting tool, this is workpiece that I am machining, this whole thing is not going to be exposed to same temperature. Temperature will be different over here, different over here, different over here, and as you go away from these points, its magnitude will further change, right? So this thing that we are saying, whenever there is increase in temperature, there is going expansion of material. So if temperature is going to be different at different locations, this expansion is also going to be different. Okay. Now, as variable expansion is there, when you machine certain component by using a cutting tool in such a variably expanded condition, it is most likely to get a worst accuracy component. Why worst accuracy component? Because if you remove material from the workpiece which has got expanded because of heat, and we know that once it is going to cool, it is going to further contract. So it is most probably you are not going to get the desirable accuracy. Desirable dimensions will not be there. The dimensions would be deviate from the actual value. So this could be the another thing that will happen because of the temperature change. So causes uneven dimensional changes in a part being machined because of the thermal expansion. Then next, induce thermal damage and metallurgical changes. Now for this one, you need to go to metallurgy and think of the heat treatment processes. So when you heat material above critical point, above recrystallization point, and then you cool it, either cool it rapidly or cool it slowly. Whenever the material undergoes this heating and cooling cycle, there will be certain microstructural changes. And we know that the properties possessed by any material are dependent of the microstructure that it has. If microstructure changes, those properties are going to change. Okay. And when you select a workpiece material, we must have thought of the properties of that material before selection. And after machining, if those properties are changing, then that is not going to be desirable, right? So that metallurgical changes would be there, and in most of the cases that will not be desirable. Additionally, the thermal damages induced by that um, heating and cooling cycles, that is also not desirable, because that thermal damages may be in the form of thermal stresses, cracking of the surfaces, and that is going to reduce the life of the component. Okay, so these are the various effects of the heat generation. Now, if we talk, as we discussed all these effects that we could observe in metal cutting, let me tell you that the suppose there is total amount of heat generated in metal cutting. Out of that total heat, only 10% of heat is going to cause this. Why? Because 90% of heat will be taken away by the chip. When you use single point cutting tool to remove the material, when workpiece material gets converted into chip and it goes away from the cutting tool and workpiece, it takes away 90% of the total heat generated. Okay, so there might be multiple choice question based on this one. What amount of heat will be taken away by the chip? So what amount it takes? 90%. So remaining 10% is the heat that is supposed to dealt by the cutting tool and workpiece. So whatever effects that we discussed over here, those effects are a result of that 10% heat only, because 90% of the heat is being taken away by the chip along with it, right? So remaining 10% heat will be taken by workpiece and cutting tool. Now out of that 10%, around 6 to 7% will be taken by workpiece, and 3 to 4%, I don't know, I don't remember exact value of that one, but 6 to 7% will be uh, absorbed by workpiece, and 3 to 4% will be absorbed by the cutting tool. Or I think this value will further drop by some digit. Okay, because minimum amount of heat will be absorbed by the cutting tool, then workpiece, and then chip. Okay, now 90% is taken away by the chip, remaining 10% is going to be absorbed by the cutting tool and workpiece. Nachiket, turn off your video. And this 90% can be further increased, means already 90% of heat is being taken by the chip, and we can increase that amount further. How we can increase that amount further? If I increase the cutting speed, what will happen if I increase the cutting speed? If I increase the cutting speed, the proportion of heat taken by the chip will further increase. Why this will increase? Because when you increase the cutting speed, that means the velocity with which chip is going away from the tool and workpiece will further increase. So if this speed increases, the time provided for dissipation of heat from chip to tool and chip to workpiece will further decrease. So by increasing the cutting speed, we will further decrease the time required to dissipate the heat from chip to workpiece and chip to tool. And that way we can increase this 90% further by increasing the cutting speed. Okay. Next, now we talked about the effects of heat generation. Now, why this generation of heat is there and how exactly it generates. For that one, we need to take a look of this sketch so that you will get a better idea. So there are certain regions where actual heat generation is there. Those regions are, first one is this AB. This AB zone is called as primary deformation zone, or it also called as shear zone, because material shearing takes place across this zone. So this is one of the source of heat generation. Second, BC. This BC is called as secondary deformation zone. Those two zones are there causing the heat generation. In addition to those two, third zone BD, that is a small zone, and this zone comes into picture when the cutting edge of the cutting tool has got worn out slightly. When this cutting edge worns out slightly, some portion of finished workpiece over here starts coming in contact with the cutting tool. So certain rubbing will be there between cutting tool and finished workpiece surface, and because of that rubbing, this third zone comes into picture. So heat generation will be there in this primary zone, then this secondary zone, and in some cases in this third zone. Okay. Additionally, whenever you deform the material, suppose this is a actual material and I started pulling this material by holding it on the either side. If I keep pulling and its dimension changes to this much, and suppose this material has got certain elastic properties, so when I remove this P, it returns back to its original state. Okay. Now, whatever energy I provided to have this elastic deformation, because on removal of the forces, it can return back to its original dimensions. So whatever energy I input for this elastic deformation will be stored in the material in the form of strain energy. Okay. So if elastic deformation is there, energy is converted into strain energy. Reverse to that, if I stretch it beyond this point and suppose after that it deforms plastically, so now this is a permanent deformation. In case of plastic deformation, whatever energy I have provided, all the energy gets converted into heat. Okay, let's continue. The last session we covered introductory part of this unit number 3, that is based on thermal aspects, tool wear and machinability. And we were discussing the reason behind the temperature generation in metal cutting and exactly how that temperature is generates, that we were discussing, and in between that session got ended. So let's begin with this point again. So in metal cutting, when you use a single point cutting tool to remove the material from the work surface, during chip formation, there are certain regions where maximum stresses are developed. Those regions are called as primary deformation zone, secondary deformation zone, and there is one more additional zone that comes into picture when we have a certain amount of tool wear. So the first zone is this AB, that represents a primary deformation zone, and that we also called as shear zone, because shearing of the work material while formation of chip takes place along that plane, and that zone is called as shear zone or primary deformation zone, that is AB. Second one is this BC zone, that zone is called as secondary deformation zone. And the third one is when there is a certain amount of tool wear, the flank face of cutting tool over here starts rubbing with the finished workpiece surface. This surface is a finished workpiece surface because tool is going to move in this direction while removing the workpiece material. So certain portion of the cutting tool starts rubbing with the finished work surface, and that results into heat generation because of the friction between those two. So that is the third zone, that is called as BD. Out of those three, this primary and secondary deformation zone are the prominent one, and third one is also there, but that is uh, comes into picture once the certain amount of tool wear is there. Now those are the various zones. Now what is the reason of the heat generation that we were discussing? So I was explaining this one with a small sketch. There is certain part that is being pulled by applying to opposite forces, and because of that one, if part get extended by this much length, and after you remove this force P, suppose that returns to its original dimension. So that kind of deformation, we know that that is a elastic deformation. Okay. Now, if I keep applying this force P beyond this point also, there would be a permanent deformation in the workpiece. And when you remove this P, this object is not going to gain its original dimensions. And that's why we call it as a plastic deformation. So whenever you apply force on a material, there are two types of deformation. First one is elastic and second one is plastic. So as long as this elastic deformation is there, the applied energy in the form of this force P, whatever energy you apply to that material, that whole energy will be stored in the material itself in the form of strain energy when it is a elastic deformation. And as all the energy is stored in the material in the form of strain energy, there will not be generation of any heat when when there is a elastic deformation. Okay, now reverse to that, whenever there is a plastic deformation. And before explaining this one, we need to remember this, that the chip formation is completely a plastic deformation. There is a very small elastic deformation and that usually is neglected. So everything is deforming plastically. Now what happens in plastic deformation? Whatever energy you provide to have that deformation, that whole energy gets converted into heat. When there is a plastic deformation, all the energy provided gets converted into heat energy. And as I just said, in metal cutting there is a dominance of the plastic deformation compared to elastic one. So all the energy provided in metal cutting gets converted into heat energy. Okay, that's the reason why in metal cutting there is a generation of heat. And how, that I already have explained. There are three deformation zones: A, B, B, C, and BD. And these three zones act as a source of heat generation. So first heat generation will be takes place in this zone, then in this zone, and then third zone BD. Okay, next, distribution of the temperature. Now you need to relate this sketch with again this sketch. So I hope you remember this sketch so that you will understand the next sketch in a better way. So this is a cutting tool. This is uncut chip thickness that after forming into chip, that becomes TC, that is chip thickness, and it flows along the rake face of the cutting tool. This is a rake face. Okay, and below this horizontal line, this is a raw material that is not going to be cut at all. And if you follow this horizontal line beyond this point, you will get the finished workpiece surface. Now in this sketch you need to focus on 3 points. The first one, point X over here, second point Y over here, and third one, point Z over here. Okay, now we know that this X point is at the top surface of the workpiece, and when, because of relative motion between tool and workpiece, when this gets converted into chip, this point is going to follow this dotted line path. Okay, this X point will pass along this line and it will be separated from the workpiece. Okay, that is for X. Second point is Y, that is at the almost at the bottom of the uncut chip thickness. This much material is to be removed or gets converted into chip, and X is at the top whereas Y is at the bottom, but that is also going to be part of chip, so it will follow this path. Okay, and the third one, that is going to be a part of workpiece, but that is almost at the surface, so it will remain in workpiece and it will follow this path. So Z will transfer along that line. Okay. Now, when you consider point X, now this is our primary deformation zone or shear zone. This is secondary deformation zone, and this is third deformation zone BD. From this sketch, this AB, BC, and BD. Those three zones we have highlighted in this sketch also. Now, if you consider point X, that passes through primary deformation zone only. If you consider point Y, that passes through primary deformation zone, then secondary deformation zone also. And third point Z, that passes through that third deformation zone that comes into picture when there is a tool wear or certain amount of tool wear is there and the cutting tool has started rubbing with the workpiece surface. Okay, so this Z passes through that point only. Now if you look at the temperature range in primary deformation zone, maximum temperature is up to 660 670 degrees Celsius. This is not an exact amount. If you change the cutting tool, change the workpiece, these values are going to change, or if you change the machining conditions, these values are going to change, but overall distribution is going to be like this one. So there would be certain temperature range over here. So when this X point passes through this zone, the maximum temperature of this surface could range up to 680. Now, if you look at the point Y, it passes through primary deformation zone. So its temperature obviously going to reach this 680. Additionally, when it passes through secondary deformation zone, its temperature increases further. And that increase might be up to 750 degrees Celsius. So Y passes through primary deformation zone as well as secondary deformation zone. And that's why at certain distance from the cutting tool edge along the rake face, you will get maximum temperature. If you observe this gauge, maximum temperature is over here. Why? Because when material reaches this point, it passes through primary as well as secondary deformation zone. So it has exposed to two heat sources in primary deformation zone and in secondary deformation zone. So maximum temperature you will get at a certain distance from the cutting edge along the rake face. Okay, remember this one. There could be a MCQ on this one also. Then third one, point Z. So when point Z follows this path, when it reaches somewhere here, the heat get conducted from this primary deformation zone into the workpiece. So it absorbs some heat over here, and when it passes through this secondary deformation zone, there would be addition of some more heat, and then it continues to remain into the workpiece surface. But remember, this point Z is almost at the surface of the workpiece. So only surface of the finished workpiece will be exposed to this much temperature. And as you go down into the workpiece, the temperature is almost remains unchanged. Okay. So this will be the nature of temperature distribution in metal cutting. Now, if I am providing PM, that is energy required in the metal cutting. So you suppose I am removing certain amount of material. For that total material removal, whatever energy I am providing, that total energy will be indicated by this PM. Now this PM will be utilized, or PM is going to be converted into heat, and that heat will be taken away by three things. What are the three things? First one, phi C, the amount of heat taken away by the chip, that is denoted by phi C. Then second, phi W, the amount of heat taken away or absorbed by the workpiece. And third one, phi T, is amount of heat gets absorbed by the cutting tool. So whatever heat is going to be generated in metal cutting, that will be taken by chip, by workpiece, and by cutting tool. Now out of these three things, that is phi C, phi W, and phi T, this phi T is going to have a minimum value, because we know that this phi C is almost 90%, and whatever remaining 10% is there, that will be addition of those two. This we know. Okay. Now out of this also, this phi T is going to have minimum value. Why? Because when chips flows along this uh, rake face of the cutting tool, the velocity of chip will be very high, and that will, or because of that high speed, that will be in contact with this rake face for a very short duration, and that won't allow much heat to be penetrated into cutting tool. And that's why this phi t is going to have minimum value, and in most of the cases that phi t will be neglected. Okay, the phi t forms a very small proportion of PM, and that will be neglected. But in some cases that we consider when the cutting speeds are very low. If I decrease the cutting speed, the velocity of chip is also going to decrease. So chip will remain in contact with the rake face for little longer duration, and that will allow more heat to be penetrated into the cutting tool. And in such a conditions, this phi t will be considered. But if this cutting speed is high, this phi t will be usually neglected. Any doubt, any query till this point? Okay. Effect of cutting speed. Now we just saw the temperature distribution in metal cutting. Now we are going to relate that temperature with cutting speed. Now to relate those temperatures with the cutting speed, we are going to consider two prominent zones, because we know that there are three zones. What are those three zones? First one, this primary and secondary, and the third zone comes into picture when there is a certain amount of tool wear. So we are not going to consider this third one. So two zones we are going to consider. First one, shear zone. So that shear zone will accept the heat phi s, and second one somewhere here along the rake face, and that is going to be addition of heat generated over here as well as heat generated on that secondary zone itself, because when material reaches the secondary zone, it already have passed through primary zone also. So addition of primary plus secondary will be the result of temperature in secondary zone. So those two going to relate with the cutting speed. So first one, mean shear zone temperature, that is in this zone, and second, mean tool face temperature, that is this one. So temperature in this zone and temperature this zone with respect to cutting speed. So when you increase cutting speed, if you consider the first one, that is phi s, temperature in this primary zone. So when you increase the cutting speed, that increases slightly. That increase is not that much. You can see temperature along this y-axis and cutting speed along this x-axis. So when you increase the cutting speed, temperature in this primary zone increases slightly, and after that it almost remains constant. So there is slight increase in temperature and then it remains constant. That is in case of primary shear zone. Now when you consider the second point, that is along rake face, its temperature with cutting speed keep on increasing only. So there is a continuous increase in a temperature on mean, that temperature we call mean tool face temperature or temperature along the rake face of the cutting tool. That temperature keeps on increasing with increase in the cutting speed. So that is the relationship between the cutting speed and temperature. Next, now till now we have seen effects of temperature, causes of temperature, temperature distribution. Now we are going to discuss various methods employed to measure the temperature in metal cutting. There are three prominent methods that are used to measure the temperature. The first one is work tool thermocouple. Now, before discussing this one, you need to brush up the concept that we studied in the subject thermodynamics. There we have seen the thermocouple. So, in thermocouple, what we do, we take two dissimilar metal wires, and then we connect them together. Okay, and what we do, we held one common point at some reference temperature and another common point or another joining point of those two dissimilar metal wires will be in a contact of body whose temperature is to be measured. Okay, this reference point will be usually at atmospheric temperature or 0 degrees Celsius. Now because of that one, what happens, this reference junction will be at some different temperature and this measuring junction will be at some different temperature, because this is in a contact with the body whose temperature is to be measured, and this reference junction has held at some reference temperature, and because of difference in those two temperatures there will be generation potential difference, or there is a development of voltage across this whole circuit. Now, if you correlate the amount of voltage developed with respect to body temperature, then you can use this whole system for the temperature measurement. So this is basically a thermocouple. The working principle of this thermocouple is called as Seebeck effect. Okay, that we are not going to talk much about, but this works on this Seebeck effect, and this is the overall working principle. Now, how to use this thermocouple in metal cutting to measure the temperature? So the first method is work tool thermocouple. So from the name itself, you will get an idea that workpiece as well as tool are going to be a part of thermocouple. That's why this is called as work tool thermocouple. If you look at this sketch, this is the cutting tool connected in an electrical circuit. This is workpiece that is going to have rotary motion. To maintain the electrical contact, this mercury slip ring will be used, and that way the workpiece will be also connected into the electrical circuit. Okay, so now when you start removing the metal, or as you begin with the machining, the temperature over here will start increasing, and with increase in temperature there will be change in voltage in the circuit. And if you calibrate those two, that is increase in temperature and development of voltage, if you correlate those two, you can use this system to measure the temperature. Okay, now this system has got certain advantages as well as limitations. Advantages is you just need to connect cutting tool and workpiece into the electrical circuit, and your temperature measurement system is ready. But there are certain limitations. What are the limitations? Here, I am making cutting tool as well as workpiece as a part of temperature measurement system. So if I change the cutting tool, the whole system has to be recalibrated, because as I change the cutting tool, this voltage generation rate is going to change because the material has changed. Similarly, if I change the workpiece material, again the system has to be recalibrated. So every time when you change either cutting tool or workpiece material, this system has to be recalibrated, and that is going to be a time consuming one. Okay, that is the first limitation. Second one, usually in thermocouple we take wires of two dissimilar metals, but here instead of taking wires, what we have done, we have taken work cutting tool as well as workpiece, and those two we have connected into the electrical circuit. But this cutting tool as well as this workpiece are not considered to be ideal materials for thermocouple. Okay, why? Because when you consider, or when you uh, make this cutting tool and workpiece as a for part of temperature measurement system, there are chances of errors. Why there are chances of errors? Because when you start machining, one of the end of this cutting tool will be fixed, and end is going to be in a contact with the cutting tool. So during machining, this cutting tool will be under strain. Similarly, this workpiece, this end will be fixed. This will be cantilever one in a rotary motion. So this one will be under the strain. And when material is under strain, this rate of voltage generation is going to be different compared to material is, or this strain is not there. If the strain is not there, the voltage development rate is going to be different, and under strain condition, this rate is going to be different. Because of that one, there are going to be chances of errors in the temperature measurement. Okay, so these are the, or this is the working principle of certain limitations associated with the work thermocouple. Now, to overcome these limitations, the next system is direct thermocouple measurement. Now, what we do in the direct thermocouple, instead of making this cutting tool and workpiece as a part of uh, temperature measurement system, Now we have made a separate arrangement for the temperature measurement. So there will be one, uh, or simply consider this as a metal wire. So that metal wire will be brought in contact with the workpiece whose temperature is to be measured, and that would be connected into the electrical circuit. So tool is now not connected into the electrical circuit. And here, as separate wire has been used for the temperature measurement, the strain rate or strain in cutting tool or strain in workpiece is not going to affect the accuracy of the temperature measurement. That is the first advantage. Second advantage, whether you change cutting tool or you change workpiece material, this wire is going to be. So with change in cutting tool or workpiece, this whole system need not to be recalibrated again and again. For accuracy, we usually calibrate system after certain period of time, but that is usual practice. But when you change either workpiece or cutting tool, the system need not to be recalibrated because measurement system has not changed. Okay, that is the next advantage. Additionally, there was one more limitation associated with this work tool thermocouple that I forgot to mention. When you use this system for temperature measurement, you will get maximum temperature in metal cutting. Means whether that temperature has maximum value over here, we don't know anything about that. Or what is the nature nature of temperature distribution, that you will never come to know. Because what we have done, we have connected one wire to the workpiece and one wire to cutting tool and one wire to the workpiece. So you will get value of maximum temperature in the metal cutting job. But when you want to have that temperature distribution, you need to go for this direct thermocouple system. Because what we can do now, if I want to measure the temperature somewhere along the tool, so I will take one more wire and I'll connect that to cutting tool at that particular position. Along tool itself, I want to measure temperature on this end. Then I will take a one more wire and connect to that point. So that way you can use multiple thermocouples, not in the same system. You will have to use separate systems, but that way you can connect number of measuring points wherever required on the workpiece or on the cutting tool also. And that way you can get the temperature at any point on the cutting tool or workpiece. So that way you will get the temperature distribution also in case of this direct thermocouple measurement.